Pluto, once recognized as the ninth planet of our solar system, is a distant, enigmatic, and relatively faint celestial body, although it was reclassified as a dwarf planet. Pluto has recently re-entered the spotlight due to groundbreaking claims by prominent astrophysicists such as Neil deGrasse Tyson and Miyoku. These experts have raised the possibility of Pluto being on a potential collision course with Neptune, a scenario that has sparked both scientific debate and public curiosity. But how realistic is such an event, and what could the consequences be? Could we be on the brink of witnessing an unprecedented cosmic phenomenon? Or is there a deeper explanation behind these alarming predictions? Join us as we unravel the mysteries of Pluto's orbit and explore the feasibility and implications of a possible Pluto-Neptune collision. Although Pluto was demoted from full planetary status, it remains a captivating object of study. Recent speculation from leading astrophysicists suggests that Pluto's orbit may be dangerously close to Neptune's. Tyson and Miyoku warned that this proximity could one day lead to a catastrophic encounter between the two celestial bodies, an event with potentially serious implications for the solar system and possibly even Earth. But how could such a collision happen? Pluto's path around the Sun is unlike that of any other planet. It takes a staggering 248 years to complete a single orbit, and since its discovery in 1930, it has yet to complete one full revolution. Its orbit is highly elliptical, far more stretched out than the nearly circular orbits of the major planets. Adding to the complexity, Pluto's orbital plane is tilted at a steep 17 degrees angle to the rest of the solar system, making its trajectory far more erratic and unique. One of the most intriguing aspects of Pluto's orbit is its interaction with Neptune's. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune does, seemingly defying the expected cosmic order. Naturally, this leads to an obvious question. Why haven't Pluto and Neptune ever collided? The answer lies in the fascinating dance of gravitational mechanics. After Pluto's discovery, astronomers worked to decipher its strange orbital behavior. Unlike the more orderly paths of other planets, Pluto's steep inclination and irregular shape made it a puzzle. Yet, despite the fact that its orbit intersects Neptune's, Pluto's motion remains remarkably stable, thanks to the complex gravitational interplay among the Sun, Neptune, and Pluto itself. This phenomenon is best understood through the lens of the three-body problem, a classic issue in celestial mechanics. It describes the difficulty in predicting the movement of three gravitationally interacting bodies. In Pluto's case, it's this problem that helps explain the intricacies of its long-term stability. One key stabilizing factor is non-concurrent libration. In simple terms, this means that although Pluto and Neptune's orbits intersect, the two bodies are always at least 90 degrees apart in their respective positions when this happens. This angular separation ensures that they never come dangerously close. Another protective mechanism is orbital precession, the slow vertical oscillation of Pluto's orbit over time. When Pluto approaches its nearest point in Neptune, it's usually well above Neptune's orbital plane, minimizing the risk of collision. Additionally, there's a lesser-known but crucial phenomenon known as the VSK wobble, named after researchers Zell, Kai, and their team. This concept explains how gravitational tugs among celestial bodies cause periodic oscillations that, paradoxically, contribute to long-term stability. Even though Pluto's orbit appears chaotic, these gravitational wobbles help maintain its relative balance over millions or even billions of years. Ultimately, these complex dynamics, non-concurrent libration, orbital precession, and gravitational wobbling, combine to create a surprisingly stable configuration. Pluto's orbital path may seem erratic, but beneath the chaos lies an elegant mathematical rhythm that protects it from colliding with Neptune. In fact, detailed numerical simulations from the late 1980s confirmed that despite all these apparent dangers, Pluto's orbit remains secure for the foreseeable future. Pluto's orbit is actually quite erratic. Small changes in its initial conditions can lead to drastically different paths over long periods. However, simulations have also demonstrated that despite this apparent chaos, Pluto's orbit remains stable over immense timescales, stretching millions or even billions of years. To understand the orbital relationship between Pluto and Neptune, we must consider the gravitational influence of the giant outer planets, Neptune, Jupiter, and Saturn. Neptune plays a particularly critical role by maintaining a special gravitational resonance with Pluto. For every 2 orbits Pluto makes around the Sun, Neptune completes 3. This 3:2 resonance helps prevent close encounters and keeps Pluto's orbit relatively stable. But Neptune isn't acting alone. Jupiter's immense gravitational pull also contributes to stabilizing Pluto's path, and Saturn plays a secondary, yet important role in this delicate celestial balancing act. These gravitational forces work in harmony to ensure Pluto stays on a safe trajectory, avoiding any direct collision with Neptune. Without such stabilizing mechanisms, our solar system could be far more chaotic. Planets might collide, or even be ejected from their orbits, leading to catastrophic consequences. The idea that Pluto might one day collide with Neptune underscores the incredible complexity of celestial mechanics. Understanding these dynamics not only helps us appreciate the fragility of planetary orbits, but also deepens our knowledge of how the solar system functions. Despite its irregular path, Pluto's motion is a perfect example of the fine balance that governs the cosmos. The concept of orbital chaos explains how sensitive an object's orbit can be to its initial position and velocity. For Pluto, even minor shifts in speed or direction could radically alter its long-term path. Scientists rely on automated simulations to study these gravitational interactions. These models show how even the tiniest change in starting conditions can lead to vastly different orbital trajectories. While Pluto's orbit is stabilized through mechanisms like resonance and precession, it remains inherently unpredictable over extremely long periods. This unpredictability makes forecasting its distant future incredibly challenging. Even so, the simulations affirm that Pluto's orbit is generally stable on geological timescales, suggesting that order can emerge even from apparent chaos. Predicting the motion of celestial bodies, especially those with eccentric orbits like Pluto, is a daunting task. The precision of these predictions depends on how accurately we know the starting conditions. A small margin of error can lead to completely different projections, making long-term forecasting uncertain. Beyond the science, Pluto's orbital behavior reflects the dynamic and ever-evolving nature of the universe. Despite the advances we've made in astronomy, Pluto reminds us how much remains unknown. Studying how the giant planets influence Pluto's orbit offers valuable insights into the interconnectedness of planetary motion. So why are astrophysicists still discussing the possibility of a future collision between Pluto and Neptune? Despite all the stabilizing forces at work, the sensitivity of Pluto's orbit continues to intrigue scientists. Neil deGrasse Tyson, renowned astrophysicist and one of the figures behind Pluto's reclassification from planet to dwarf planet, offers a compelling viewpoint. He sees Pluto's complex orbital behavior not as a threat, but as a fascinating puzzle that highlights the mysteries still hidden within our solar system. In exploring Pluto's role in the ever-evolving landscape of our solar system, Neil deGrasse Tyson doesn't view its reclassification as a demotion, but rather as a necessary refinement, an outcome of our growing understanding of space and celestial mechanics. For Tyson, celestial mechanics is a field in constant flux, where discoveries reshape our understanding. Pluto's complex and eccentric orbit serves as a reminder of just how much remains to be uncovered. Although Tyson is optimistic about space exploration, his views on the hypothetical collision between Pluto and Neptune reflect the many unanswered questions that still linger. Could Pluto truly be on a collision course with Neptune, or is this simply a misunderstanding within the broader cosmic choreography? Only time and further study will reveal the truth. What's certain for now is that the mystery deepens our curiosity and drives continued investigation into the dynamics of our own solar system. The idea of Pluto colliding with Neptune raises profound questions about gravitational interactions and how they shape planetary motion. Such a collision between a frozen dwarf planet and a massive gas giant would carry immense implications, possibly observable from great cosmic distances. To assess this possibility, it's crucial to understand the nature of both planets. Pluto, though small, is composed of various frozen elements, including nitrogen, methane, and carbon monoxide. Neptune, by contrast, is a hydrogen and helium-rich gas giant with a thick atmosphere and immense gravitational pull. Yet, Neptune's gravity isn't acting alone. Jupiter, the solar system's largest planet, also plays a stabilizing role in Pluto's orbit, along with Saturn's gravitational influence. These forces create a dynamic interplay that makes a catastrophic collision between Pluto and Neptune highly unlikely. In fact, the gravitational relationship between Pluto and Neptune is defined by a resonance. Specifically, for every 2 orbits Pluto completes, Neptune completes 3. This 3:2 orbital resonance forms a kind of cosmic safeguard, ensuring that their paths, while crossing, never result in an impact. This gravitational synchronization has often been described as a celestial dance, an elegant example of balance amid the chaos of space. However, this balance isn't set in stone. Even slight alterations in velocity or orbital position, caused by internal mechanisms like tidal forces or external influences, such as a passing star, could eventually disturb this resonance. Some researchers have even proposed that an undiscovered planetary body, often referred to as Planet 9, might be exerting subtle gravitational forces on outer solar system objects like Pluto. If real, its presence could disrupt current orbital configurations and introduce new instabilities. Adding to the complexity, the Sun itself is slowly losing mass via solar wind, causing planetary orbits to gradually expand. Over long timescales, this could subtly shift the dynamics between Pluto, Neptune, and the rest of the solar system. Furthermore, the outer solar system is not a quiet, unchanging realm. Comets and minor objects frequently pass through, each with the potential to apply slight gravitational nudges that could ripple through orbital systems. In this ever-changing environment, Pluto's orbit remains dynamic, shaped by the constant gravitational interplay of the solar system's major and minor players. Continued observation and advancing technology will help refine our understanding of these complex relationships. Whether or not Pluto and Neptune will ever collide, their interaction serves as a fascinating case study in the intricate dance of planetary dynamics and the broader forces at play in our solar system's evolution.